All right, we're starting now. Hello, everyone. This is Bob Dugan from Chelsea Communications. Today, we are going to be demonstrating the RYUSI MoSMB SMB3 server, and we're going to be connecting it through Windows 10 client. All this over RDMA, and in particular, IWARP version of RDMA using Chelsea adapters on either end. Let me do some introductions first. We're very honored to have Ned Pyle, Principal Program Manager from Windows Server and Storage at Microsoft, joining us. He'll be talking about Windows 10 RDMA, Azure Stack HCI and Storage Spaces Direct, Storage Replica, and Scale Out File Server. We're also honored to have Sandeep from RYUSI. He will be talking about the MoSMB server, SMB3 server, which enables high-speed, low-overhead media and entertainment workflows. This product runs on Linux, which is a little bit different because it is running SMB Direct, which is a Microsoft protocol. So now this has been ported over to Linux, and this is one of the first, if not the first product out running Linux. And as I said, I am Bob Dugan, Director of Engineering at Chelsea, and I'll be talking a little bit about Chelsea, about our products, and then finally about the IWARP technology we have embedded in our ASIC in our adapters. IWARP is a flavor of RDMA, and I'll contrast that a little bit with other flavors of RDMA.
I'll be talking about enabling high-speed, low-overhead media and entertainment workflows using the combined solution. So let me start by giving a quick introduction to a company, RYUSI, and a product, MoSMB. So RYUSI is a product development and consulting company, and we are focused on data storage. So our flagship product is MoSMB, which stands for SMB with Mojo, and it is an SMB server on Linux. So we have partnered with Microsoft to license their IP related to SMB protocol and built MoSMB based on this IP. So MoSMB comes in two flavors out of box. The first runs on POSIX file systems like XFS, ZFS, and also distributed file systems like CephFS and MapRFS. The other works on ST-compatible object storage, such as Scalability and Minio. We also have a plugin architecture to support custom storage backends with proprietary interfaces, and we can also have all of these different plugins coexist on the same server. So you could have one share based on POSIX file system, the other on ST object storage, and the third one could be based on some proprietary storage, and you could easily move files across these different shares by just dragging and dropping them. So MoSMB is architected for high scalability and high availability. We support persistent handles and witness server for transparent failover and continuous availability. We support scale up also, but we also support scale out architecture for horizontal scaling. We have a fairly rich feature set, which includes signing, encryption, AD Kerberos authentication, Windows and POSIX ACLs, SMB Multichannel, and quite a few other features as well. So this set of features makes it well suited for a lot of enterprise use cases. Finally, MoSMB also leverages the network offload capability of SMB Direct or RDMA to free up CPU, and therefore provides more headroom to compute intensive video applications like DaVinci Resolve, Adobe Premiere Pro, Final Cut Pro, etc. Moving on, I just also want to talk about some of the unique storage challenges that media and entertainment workflows pose. So MED workflows are amongst the most demanding in terms of storage. The workflows, they combine video editing, adding visual effects, sound mixing, color correction, and many other stages before the content can make its way to TV or big screen. All of these stages are highly IO intensive. The situation is further aggravated by new video resolutions of 4K and higher, multi-camera mode of production, and advanced visual effects, which further increase the need for high performance storage. It is not just the IO intensive tasks which need to be there. Post-production tools also need to perform a lot of CPU intensive tasks like encoding, decoding, transcoding, and rendering in real time, while the video ingest and playback happens at fairly high FPS rates in the background. So one other aspect is that creative work is collaborative in nature and it is storage centric. Typically, teams are geographically dispersed and they need access to high-speed NAS for collaborating amongst themselves. Finally, a lot of M&E companies need to leverage industry standards so that they can avoid vendor lock-in and keep the costs low. So some of these industry standards include Ethernet for connectivity and SMB protocol for NAS access. So I will go on to show how this combined solution that we are talking about addresses some of these storage challenges. So moving on, we have a demo plan. So it's a recording, it's not a live demo, but for the setup, we had two nodes. The first of these is a Windows 10 enterprise client, and the second one is an RHEL 7.6 server with MoSMB running on it. These two were connected with Chelsio 100 gig IOP RDMA network adapter. For storage, we had used NVMe disk, and we had XFS file system, which is a fairly standard file system running on top. So essentially, we had a single Windows SMB client connected to standalone MoSMB server with Chelsio IOP RDMA NIC cards. Excuse me. So our demo objectives were as follows. The first goal was to demonstrate a combined solution that would offer high throughput as is needed by IO intensive video playback and video ingest workloads. We used disk SPD to simulate the video workloads. We also validate that the combined solution is low on CPU utilization. The second goal was to demonstrate parallel high-speed 4K video ingest and video playback with zero dropped frames. We used a frame test to simulate 4K video workloads. For this goal also, we validate that the combined solution is low on CPU utilization. Finally, we also established the savings in CPU cycles for video playback over RDMA transport versus TCP transport, thereby providing additional CPU headroom for compute-intensive video applications. So I'll move on to the first demo. So we have done this demo using disk SPD for the video playback scenario. I'll just start this video. So as you can see, here we are seeing a throughput of around 93 to 94 gigabits per second, and the CPU utilization is just about 5%. The throughput is fairly steady, as you can see, and it is sustained for the entire duration of the run. So I'll just summarize the disk SPD findings. So with the combined solution, we could achieve a throughput of 94 gigabits per second for the simulated video playback workload. We could also achieve a throughput of 76 gigabits per second for the video ingest workload. The CPU utilization was fairly low in both cases, just around 5 to 6%, and the throughput was sustained throughout the entire run. And this is critical for M&E workflows because you obviously don't want to have any dropped frames. So I'll move on to the second demo. So here we ran 4 frame test instances so as to simulate 4 parallel streams of video playback. Here we see that the throughput is around 45 to 50 gigabits per second, and the CPU utilization is fairly low again, just around 5 to 6%. We will also see the frame rate that we achieve for these 4 instances of frame test. For the first instance, we see that the FPS is around 29. For the second one, it is around 31. For the third one, it is around 29 again. And for the fourth one also, it is around 29. So I'll just come to the findings. So we could achieve 4 parallel simulated video playback workload with 29 frames per second for each 4K stream. For video ingest, the frame rate was 25 frames per second. The drop frames were 0 in both the above cases, and the CPU utilization was fairly low again, just around 5 to 6%. The throughput was also sustained for the entire duration. As you will also realize, the throughput was just around 45 to 50 gigabits per second, and the CPU usage is again, just around 5 to 6%, which means that there is enough headroom on both the CPU side and the network bandwidth side, which means that you could run some compute intensive applications in parallel, or you could also use the network bandwidth to run additional video streams. So currently we were running 4 in parallel, but we could probably go up to 6 or 7. So moving on, we repeat the same test, but for TCP as the transport mechanism. So I'll just start the video. So here we see that the throughput is between 40 to 45 gigabits per second, but the CPU utilization is fairly high. It's around 19 to 20%, and that is almost 4 times as much as for RDMA. So I'll jump onto the findings. So these are the findings. We could achieve 4 parallel streams running at 26 frames per second for each stream, which is fairly good. The drop frames were also 0, but the CPU utilization was much higher as compared to RDMA, almost 4 times as much. So moving on, we also did one additional set of tests where we recorded the CPU cycles per byte over RDMA versus TCP. We used disk SPD as the tool here, and we got the readings for different block sizes. What we could see is that the CPU cycles per byte were almost 8 times as high for TCP versus RDMA. What this led us to conclude was that the use of IOP RDMA as transport can create significant CPU headroom for compute intensive media workloads. And that is a key advantage of using RDMA over TCP. So I go to my final slide. So overall, what we saw was that there are a lot of challenges with cutting edge media workflows for the storage, but the combined solution, which comprised of a Windows 10 client, a MoSMB server connected with Chelsea IOP RDMA cards, could address a lot of these challenges. We could see high performance IO combined with low CPU usage. Also, the solution was based on industry standard Ethernet and standard NAS protocols such as SMB. So we believe that the combined solution could be a good option for the modern media and entertainment workflows.